Hi everyone, my video report consists of the anatomy of MIB. The anatomy of MIB is all about the discussion about the structure of management information. It simply tells about the content or the composition of MIB. In the preceding discussion, SNMP and SMI will be mentioned. SNMP stands for Simple Network Management Protocol. SNP or SNMP is an Internet Standard Protocol for managing devices on IP networks. These managed devices include routers, switches, servers, workstations, printers, modem racks, and more. On the other hand, SMI, which means Structure of Management Information, is the part of the SNMP framework that ensures the universality of MIB objects. SMI standard is responsible for defining the rules for how MIB objects are structured, described, and organized. SMI allows the similar devices to communicate by ensuring that they use a universal data representation for all management information. Structure of Management Information Overview. In SMI, MIB definitions are specified as MIB modules, or Management Information-Based Modules. A MIB module generally serves a particular purpose, such as to define management information related to devices, communication interfaces, or to a voicemail server feature that is embedded on a particular type device. Management information-based modules is just like classes in programming languages. Each class contains methods, variables, events, statements, and etc. This refers to the information about the class. As illustrated in the figure, there is the object called device MIB. The object contains different MIB modules of simple informations which will be executed whenever the object is accessed. MIB information is arranged into a conceptual tree. Every definition in a MIB module is represented by a node in that tree. Each node is named relative to the containing node. This name is also called the Object Identifier, or OID. Accordingly, the tree is commonly referred to as an Object Identifier tree. The top node in a MIB module is the definition of the MIB module, which itself registered as part of a larger global Internet Object Identifier tree. This is the illustration of MIB info in a conceptual tree. The information inside the rectangle is the Object Identifier, or OID. The figure itself is the Object Identifier tree. As far as object types are concerned, two categories need to be distinguished. Object types that will be instantiated only once in an agent. This means that there will always be exactly one instance of the object type in the MIB. Those are also called scalars. Object types that can be instantiated multiple times. This means that multiple objects of that same object type can exist in a MIB. Those are also called columnar objects because they are thought of as a column in a conceptual table that can have multiple rows, one for each instance. The system group contains a number of scalars, the object types that will be instantiated exactly once. The definition of an object type consists of several elements. The following are syntax. It defines the data type and size of the object. Access, whether the object is read-only, write-only, or both. Status, it refers to the definition life cycle. And lastly, description. It contains an explanation of the intended purpose of the object type. TCP-con table. It contains the definition of the table. It is also the first submodule of TCP group. It looks similar to the definition of scalar object types, with two exceptions. Its syntax does not designate a simple data type, but a sequence of objects of another type. Those objects are the table entries, the rows of the table. Its access clause indicates that it is not accessible. It can be neither read nor written to, so for management purposes, it carries no information on its own. It is the topmost container object for the columnar objects that make up the actual management information contained in this table. The third submodule of TCP group is the TCP-con state. It is the first of the object types that comprise the table. It is worth noting that the definition of columnar object types does not differ from that of scalar object types. You cannot tell from the definition which is which. The one aspect that makes it a columnar object type is that the containing node is a table row. TCP-con entry in the name of the object type is referenced in the sequence that is defined as part of the syntax of the table row. Instantiation in an actual management information base. Object instances in a MIB are considered to be conceptually part of the same object identifier tree as the object type definitions themselves. Those leaf nodes start growing leaves underneath them, so to speak, that constitute the nodes of the object instances. In the illustration, every scalar object type has created new scalar object, and every columnar object type has created new columnar object. That's object instantiation principle. The object identifier of a management information-based object consists of the object identifier of its object type, concatenated with a suffix to distinguish the actual object instance. As mentioned earlier, scalars need to be distinguished from columnar objects in how they are identified. Scalars have only one instance in any particular MIB. They are designated a zero identifier relative to their object type definition, which is appended to the object type's OID. Columnar objects can have multiple instances that need to be distinguished from one another. Therefore, they need to be identified differently. Simply appending a zero is not sufficient. You will recall that, as part of the table definition, an index was defined that consisted of one or more columnar object types. Now let's take a summary of the chapter report by scenario. A network administrator needs to perform two basic types of actions: gather data about devices to learn how they are functioning, and give commands to devices to change how they are functioning. In the simplest terms, the first category can be considered like a read operation, and the second is comparable to a write operation. A classical way of implementing this functionality is to define a communication protocol. Most such protocols are command-oriented. They consist of a specific set of commands to perform the read and write operations we mentioned above. For example, a network management protocol might have a read command such as report on number of hours device has been in use, and a write command such as put this device into test mode. The network manager would control the device by giving the appropriate commands. A command-oriented management protocol has the advantage of simplicity. It's clear what the commands are for and how they are to be used. It can be reasonably well suited for use in certain environments, but it doesn't work well in a large, heterogeneous TCP/IP internet network. The main reason for this is that command orientation inextricably ties the protocol to the devices being managed. Let's consider this. Every type of device might require a distinct set of commands. For example, the commands given to a router might need to be different than those given to a host. This would lead either to a proliferation of commands in the protocol or to inflexibility to allowing proper management of different device types. Every time a company created a new type of device or made a unique version of a type of device, the network management protocol would have to be changed. Whenever the operation of a kind of device change, due perhaps to a change in another protocol, the management protocol would need to be updated. The protocol itself could not be easily changed without affecting a lot of hardware. The solution to the problems of command-oriented management protocols was to use an information-oriented model, and that comes the management information base. Instead of defining specific commands that interrogate or control devices, the devices are defined in terms of units of information that are to be exchanged between the devices in a management station.